Hello and welcome to this lesson for contemporary math. We have some notes here for sets and Venn diagrams. Let's jump right in. So just as a very brief introduction, we like to play this little game here. We ask, what do the following have in common? So for 1, 2, 3, 4, and 5, go ahead and pause the video and just see if you can figure out what all of these words pertain to. So here are the first three: grass, ball, hole, club, and a capital T, tiger. Now, those all pertain to golf. The next one, football, school, Halloween, World Series, leaves. Those all pertain to fall or autumn. The third one here, archer, violinist, gift. Those all have to do with a bow. Let's see. The next one I thought was a little bit harder for myself anyway. When I first saw it, April, locker room, and bride to be. These all have to do with a shower. Go ahead and think about that for a second. Lastly, bowling alley, tailor, and a wrestling match. Those all have pins in them. So why do we do this? Because it's human nature to organize and categorize and classify things. Putting things in sets helps us organize and simplify our world, where we deal with a great amount of information. In this unit, we'll focus on propositions that claim a relationship between two categories of things. So before we go ahead and start doing that, we are going to have to also introduce what is set notation. So we would just say a set is a collection of objects. And that makes sense. If you're a collector of anything, you know you have to collect the entire set. Or maybe you can think of Pokemon, gotta catch them all. It's a set of objects. The objects are called members of the set. All right. So when we deal with sets, we can use these curly braces to encapsulate the idea of what the set is, and sometimes we'll need to use some dots to indicate a continuing pattern of the members. Let's take a look at some examples down below. So in these next three examples, I want to use braces to write the contents of each of the following sets. So here first we have the Three Stooges, and the Three Stooges would be known as Larry, Curly, and Moe. So since Larry, Curly, and Moe are the only people that made up the Three Stooges, we would list all their names, separate them by commas, and wrap it in these curly braces on the end. The next one, we have whole numbers greater than 4. Well, whoa, that's a lot of numbers. So, I guess we could just start with a number that's greater than 4. All right, I guess that'd have to be 5. So 5, 6, 7, 8, 9, 10. And I don't want to write any more numbers, otherwise I'll be writing forever. So what you can do is you can act like you're going to write the next number with a comma, and then those 3 dots that I mentioned, the pattern will continue forever. These 3 dots right up here says use 3 dots to indicate a continuing pattern. Well, that's going to continue. We put it at the end because it's just going to continue forever. For this next one, we have even numbers between 100 and 200. So what we can do is we can start at 102 because that's what the wording says. They are between 100 and 200. We do not include 100 and 200. The wording would reflect it when you need to include those numbers. So this is different from part B, and I'll show you how. So even numbers between 100 and 200, so we have 102, we need the next even number, 104, we need the next even number, 106, and really, we only need a 3-number lead-in, if you will. We only need 3 numbers to start our pattern. So 102, 104, 106. Now there are a lot of other numbers between that and when we get up to 198. So I'm going to put all these dots here this time in the middle, and we can end with 198. So that's how you could represent all of the even numbers between 100 and 200. Also up here, for this particular example here, part B, I didn't have to list out all these numbers. I only have to list out 3. Oops. So I did not have to list out 8, 9, and 10. You only have to have a pattern of 3 numbers. All right. The last little bit here, a Venn diagram is a simple visual way to describe relationships using circles. Let's take a look at this example just so you can get a feel for how Venn diagrams work. What you can see over here is that we have this big old box. And this big old box would represent all animals. Then we have this circle here, and everything inside this circle you can see is labeled mammals. So everything in this circle would be any mammal. And then this little circle here, we would consider whales. This is the group of whales. And whales, the entire bubble is inside the mammals bubble. And the tan area that's shaded out around here, those are non-mammals. It's like these circles just kind of create little barriers. Only certain things can get in the circle, mammals. Anything else, all the non-mammals, you have to stay out there. In this circle, whales. So all the whales can come in here, but none of the other mammals. So example 1 says the set of whales is a subset of the set of mammals. Every element of the set of whales is a member of the set of animals. Every whale is in the mammal bubble, so that makes every whale a mammal. Some more about Venn diagrams here. We can say the set of fish is disjoint from the set of mammals. And that means when 2 sets are disjoint, they have no members in common. There's no overlap. But you can see down here in example 3, we have the set of doctors and women are overlapping. So that just means we have a bubble full of doctors here, and that could be anybody. That could be men and women. And we have a bubble of women over here, so those are women. But since I mentioned that some doctors can be women, they will have some overlap. In this overlap, we have both of these descriptors. In this overlap are where the women who are doctors live. So all of these doctors outside of this overlap here, in this blue section, they've got to be guys. The only women doctors are in this little bubble here. Over here in this pink bubble, these are women who are not doctors because they're not in the, I guess, the overlapping region. And then everybody out here are men who are not doctors, right? Only women are in this bubble here. So everything outside of this bubble has to be a guy. And everything outside of the doctor's bubble can't be a doctor. For the last little section on this slide, I want to have you just take a couple minutes, pause the video, and see if you can come up with your own examples of sets. Sets of any two things that don't overlap or have nothing in common. Sets where one set is completely inside of another set, like the whales and the mammal example from the last slide. Or overlapping sets, so that the two sets have some members in common. Go ahead and pause the video and give it a shot. Alright, so here are some examples that I came up with, and you can go ahead and read through those. I'll be silent for about 15 seconds just to make sure you get a chance to see them all. So for the next section, we talk about sets. We talk about Venn diagrams, so we can help make sets of numbers easier to understand. And so I'm going to pause the video myself and write a bunch of things down and be back in like 3 seconds. So here goes all this information. The natural numbers are the counting numbers starting at 1, moving to 2, moving to 3, just how you would teach any little kid to count, always starting at 1. Whole numbers. Whole numbers are the natural numbers plus 0. So you start at 0, and then go to 1, and then it's familiar from there, 2, 3, 4, da da da. Then we jump up to integers. Integers are whole numbers and their negatives. So when you look over here, we have 0, 1, 2. Those look a lot like the whole numbers here. But then we also include -1 and -2 and -3 and forever to the negative side, and 1, 2, 3 forever to the positive side. Rational numbers, we have a little harder time expressing by set notation using these little braces here. So we say these are the integers and all fractions that can be created by integers. So like 3/5 is a good example, or you could have -1, which is an integer, over 1,000,000, which is an integer. So we usually denote this set by a Q with an extra little bar here. I don't think you need to know that for anything really, but I thought it's cool. Irrational numbers, numbers that cannot be expressed in a fraction with integers. So like pi, or if you've heard of the number e, Euler's constant, or the natural base they call it sometimes. Pi or e or the square root of 2. You cannot represent the square root of 2 as a fraction. So these are all of our irrational numbers. And then real numbers are the sum. If you put all of the rational and irrational numbers together in the same set, you'll get the real numbers. And some of you, if not all of you, have seen this R before, and that's how we denote what the real numbers look like as a set. And I want to point out this Q is very similar to this R, where it has that extra bar going on in there. So when you have a Q with that extra bar, like it gets that notation, it borrows the notation from the real numbers symbol. I'm going to move the page up and we can look at the Venn diagram of these sets of numbers. Okay, so here is what's going to happen. We're going to look at all of these numbers, or all of these sets of numbers, and I'm going to start out small. So the smallest set of numbers that we have that was listed up there is the natural numbers. From the natural numbers, all we did was add things to it. But you'll notice that the whole numbers include all of the natural numbers. It just adds one extra number to it, the 0. So we've got the whole numbers like this. And so just by looking at this beginning diagram that we have, all the natural numbers are whole numbers. Every number that is in this bubble was also in the whole number set if you go back or rewind the video or look at your paper or whatever. The only thing the whole numbers has that natural numbers don't is 0. So this is 0 floating around over here. The next biggest set of numbers we have is what is known as the integers. And even if you go back and look at the descriptions I had for the integers were the whole numbers plus all the extra stuff. And the extra stuff in the integers were negative numbers. Then we had, what do we have? Rationals. So all the rational numbers are sort of floating around in this bubble. But between the integer bubble and the rational bubble, these are all the fractions that we were able to produce. So if we add the fractions, we get the rationals bubble. The next bubble, well, see up in the description we had irrationals. Well, irrationals and rationals are disjoint sets. They don't overlap at all. So how we denote that is I keep expanding my bubbles out here, and I call this the real numbers bubble. So all the real numbers are in this bubble, and all of the rationals are in this bubble. That means everything between those two bubbles is where the irrational numbers are. Irrational numbers. And then lastly, this is not something that we talked about up above, but lastly we have all of these numbers in a box here. And all of these numbers just boil down to complex, what we call complex numbers. And the difference between real and complex numbers is that we add imaginary parts to our numbers. So in red, all of these things in red here are what was added to the previous bubble, the smaller bubble, to get the next one. All right, really quickly then, we have these last little bits down here. It says choose the first set in the list, natural, whole, integer, rational, real, that describes each number. So we're only going to use these as we move forward: natural, whole, integer, rational, and real numbers. So the first one, we have a fraction. It's okay if it's negative. We have integer on the top and the bottom. This would be a rational number. 0. Where was the first time we were able to see 0? Was 0 up in the natural numbers? No. Oh, here it is. 0 is what got us up to whole numbers. Let's say it's a whole number. Next, -7. Where was the first time we were allowed to see negatives? I think that was, yeah, right here, the integers. So we can call this an integer. Now, a square root of 3, that's a little tricky. So square root of 3 is not a whole number. It's not a whole number 0. It's not a natural number. It's not a whole number. It's not an integer, which are the whole numbers and their negatives. It's not a rational number because we can't express the square root of 3 as a fraction. So what it is really is it is a real number. Next, 15, that is a whole number that's positive. And we first would see that in the natural numbers. With pi over 3, anytime you see pi, that's just automatically real. And then the last one here, this would be a decimal, which can be converted to a fraction. And if you have a fraction, that would make it rational. And then really quickly down here, I'm just going to give you some answers. This is true, this is false, this is true. Go ahead and read those on your own. Pause the video, read those on your own. Sometimes when we were working with Venn diagrams, you'll be given a Venn diagram like this, and it'll be useful to be able to describe each region. So, what we are going to do is we are going to look at the Venn diagram and just sort of talk about it and then see if we can come up with the categories over here. So here we have Sanjak students in the left bubble. Here we have females in the right bubble. So I think it's easiest, this is my opinion, I think it's always easiest to start with the overlap. So in the middle here, in our overlap, part B, we have females who are Sanjak students, or female students. All right, so we've got that taken care of. So, since we used both descriptors in our middle section, if I just kind of get rid of this middle section, when we go back and only look at this section, we will say, clearly part C over here has to be females. But we also include the negation of the other bubble. So these are females, but not Sanjak students. So female, not Sanjak students. And so we have to do the same thing for this bubble over here. You can see everybody in this bubble is a Sanjak student, but we have to include the negation of the other bubble. So Sanjak students, not female, or not female just means males, so we could say male Sanjak students. And then the outside bin, everything outside of these bubbles, going all the way around like this, will be the negation of both Sanjak students and females. So the negation of female is male. The negation of Sanjak student is not a Sanjak student. And that's how it's going to work every single time. So we take the normal description, females and Sanjak students for the overlap. The overlap gets both qualities. When we start looking at one piece of this bubble without the overlap, we include the name and we negate the other. Just like we did for part A. Sanjak students is there, the negation of female is male. Or for part C, again, just a recap, females works. That's where everybody in here is a female. But we negate the other, not Sanjak students. All right, let's take a look at example 5. All right, use the Venn diagram to answer the following questions. A leasing company conducted a survey to find how many residents in an apartment complex use the swimming pool and gym facilities. Okay, so the first question is, how many people use both facilities? AKA, where do these bubbles overlap? That's a pretty easy one to start out with. It's 19 total people. Now, what does that mean? 19 people here use the swimming pool, and the same 19 people use the gym. And that's going to be important to understand when we start looking at the next question. How many of them use the gym? Well, we have 87 people here, and that's what most students tend to look at, is just this number right here. But that's not true. It's not just 87. I just got done saying that these 19 people use the swimming pool and the gym. So if you're looking to answer something for just one of the bubbles, you have to include both numbers. And so 87 plus 19 is 106 total people use the gym. It's okay that some of them use the pool too. We are just asking the question, how many use the gym? All right. The next question, how many residents use one or the other? Well, that would be everybody in here. So using or, remember, means one of them can be true. So that means people who just use the swimming pool. The other can be true, which are the people who use the gym, or both can be true. This is an inclusive or. So we would add all of these together and get 201. Let me see. 1, 2, 3. 201 people use one or the other or both. That's what this is asking you. One or the other or both. Now the last one, how many residents are in the apartment complex? Well, we already know that there are 201 people that actually use the facilities here. But then you see this number over here. These people get the negation for both bubbles. They do not use the pool and they do not use the gym. So we know 201 total people use one or other of the both, and 49 people use nothing. So that brings us to a total of 250 people living in that apartment complex. Moving on to number 6, you can see that this exercise is a little different because in the last example 5 up here, we already knew what these bubbles were referring to. They had their little titles. We knew how many people were in each bubble or how many objects or how many members each bubble had. And you'll notice down here in example 6, we have nothing given to us. So let's read and see what our options are. It says, during a buffet breakfast, 41 diners picked up cups of coffee and 33 opted for juice. 11 diners chose both. Draw a Venn diagram based on the information provided. Now, in order to draw this Venn diagram, it is easiest, in fact, it should be your first step to start out with the both. Both what? Well, it looks like our diners had a choice from either coffee or juice. So that's what our bubbles will contain. People who chose coffee and people who chose juice. Now, the 11 diners that chose both would be in the overlap. So we know 11 people would be in this middle section because 11 people are in the coffee bubble, and those same 11 people are in the juice bubble. So these people chose both coffee and juice. Then we can move over to the other options here. We know that 33 people opted for juice. What that means is that the total number of people in the juice bubble should be 33. So this bubble right here. Well, we already have 11 people in this bubble, so to figure out how many people will be not in the overlap, we just have to take these 11 people here away from the 33 that had juice. So 33 minus 11, that would leave us with 22 people who only got juice. And we do something similar over here for the people who picked up coffee. So 41 diners opted for coffee. Now again, those are the people who are just in this bubble. And what that means again is that we already know we have 11 people that chose coffee because they chose coffee and juice. That means if we take those 11 people from the 41 we had earlier, we would have 30 diners who just got coffee. So this in the middle would be people who chose coffee and, there's our little logical operator, juice. coffee and juice. So then we can answer some questions. How many diners preferred to drink only coffee? Well, now that we have all of our numbers in here and we've defined what everything means, we can answer that pretty easily. It's just going to be 30 people. The second question is find the total number of diners that were present. All we have to do is add all three of these numbers together. So we have 30 and 33. If you add those together, that's 63 total people. And then the question is how many, the last question is, how many diners did not consume coffee? Well, these 30 people had coffee and these 11 people had coffee. The only people that didn't have coffee are right here. So that means 22 people did not consume coffee, aka only 22 people had only juice. For the last example in this video, I know it's getting very lengthy and I do apologize for that. We have another Venn diagram exercise. So it says the following represents data students collected on gender and whether students had pierced ears. So again, we have these two bubbles. There are no numbers in here. We have some stuff over here. I'll get to that in a minute. We don't even need this yet. The first thing you want to do is label your bubbles. So we have it by gender. It looks like we only have two choices for gender here. So why don't we call this bubble female? We have to pick one of the genders. So what that'll mean is everything in this bubble here, all the members in this bubble will be female, and everything outside of this bubble, like this, will be male. All right, let me see if I can erase that. Next, we have whether or not the student had their ears pierced. So we can either pick yes or no. And why don't we just pick yes and say ears are pierced. So that means everybody in this bubble will have their ears pierced, and everybody outside that green bubble will have their ears, won't have their ears pierced. So the overlap here is our logical operator and. This would be female and ears pierced. So now we can start placing these numbers. Well, we know 84 females have their ears pierced, and I can tell because if I follow this number back to the left, this tells me 84 females, and yes, their ears are pierced. So we have 84 that have both. We have 4 females without their ears pierced. Again, I can just follow those back to the little categories there and there. So 4 females, they would be in this bubble, but not in the overlap because these 4 females do not have their ears pierced. These 4 females are not also in this green bubble. Next, we could take care of, let's see, what would this portion represent? I guess that would be people who have their ears pierced but are not female. I guess that'd be male. So that would be 19 people who have their ears pierced but are not female. So I can take that back, not female would be male. And yes, for the ears pierced. So we've taken care of 3 of the 4 numbers here, 19, 84, and 4. Well, the last number that we're going to deal with here, the 71, will be males without their ears pierced. So we have to be outside of the female bubble. We have to be outside of the pierced bubble. So this sort of blocks off those 71 guys without their ears pierced. So they can only be out here. And that's it. We just had to make the Venn diagram here. I hope this is very informative for you, and I wish you good luck.